let's start the discussion with the history of motion. There are three key scientists that have really affected and changed the way we think of how things move. The first is Aristotle, who just was an observer of nature, and he came up with two different types of motion: natural motion and violent motion. Now, according to natural motion, um, objects were just looking for their natural position. A boulder fell to the base of a cliff because its natural position was in the river, while smoke would rise because its natural position was high, up in the room or in the clouds even. He believed violent motion um, occurred when an object was forced to move, like when you threw a rock or you pushed a cart. Copernicus was a fascinating individual who came up with some pretty remarkable theories. At the time he lived, the popular belief was the Earth was the center of everything, and the sun, of course, went around the Earth. Now, he didn't believe that. Quite the contrary, he believed the sun was the center of our universe, and, heresy of heresies, that the Earth rotated around the sun. Oops. So, he wrote a book at the urgings of his friends, and it was published um, shortly before he died. Galileo was a very outspoken supporter of Copernicus, and he had some um, very interesting theories as well. He believed that there was something out there called friction. So if I slid a box along a floor, whoops, there was something called friction that would slow it down. And so I would need to apply some sort of force to keep that object moving. Now we all know Sir Isaac Newton, and what's fascinating about Newton is he developed his three laws of motion by the age of 24. It turns out Newton was more accurate than even Aristotle. Than Aristotle, and in many ways, Copernicus and even Galileo. He just refined these theories. Now we all know he had three laws. First law of inertia, second law is the net force law, and the third law is the action-reaction law. So let's go into those a little bit more detail. Newton's first law is usually called the law of inertia. Now, inertia is just a tendency of an object to resist its change. It's why objects do not just move on their own. Everyone knows from their elementary years that an object at rest stays at rest unless it's acted on by an outside force. So basically, things don't want to change what they're doing. Now, inertia is an interesting property. We use mass to measure inertia. The amount of inertia an object has depends upon its mass. So a 100-kilogram block or bowling ball is going to have more mass than a 10-kilogram. The more force that an object requires to change its motion, the more mass it has. Did I say that right? The more force it's required, the more mass it has, and therefore the more inertia. When more inertia has, the more mass it has. Now the second law is a realization from Newton that the acceleration an object has depends not only on how hard you push it or how hard you pull it, but also on the mass of that object. He found that a net force applied will change its acceleration in the direction of that force. So the law is stated as F net is ma. Now I like to use this Greek summation sign for summing up the forces. And so I will flop between F net being the summation of individual forces and the summation of F being the summation of individual forces. Now, Newton is a unit of force. We know that F net equals ma. we could use as a unit kilogram meters per second squared, but that's just too much work. So let's just call it a capital N, capital Newton, for ease. Now, let's look at a problem. Suppose you have an airplane that needs to accelerate at 5 meters per second squared to reach takeoff speed. And the mass of the airplane is 5,000 kilograms. All right? So we have those two pieces of information. How much force do you need? What do we know? Well, meters per second squared, that's acceleration, of course. And the 5,000 kilograms is mass. And these aren't wanting to stay. Okay? What do you need to find? Well, we're looking for how much force. How much force is... Okay, we're looking for force. So what equation? What's the equation going to look like? We always start with the first equation, F equals ma. That's where we start. And of course, what is the unit for force? The units are going to be in newtons. Now let's look at the net force. Suppose I have a force pulling 15 newtons to the right. It's very clear to see that in this case, I have a net force of 15 newtons. What if I have a force going to the left? Now my net force will be 15 to the right, so that's plus 15, minus 5 to the left, like this, or 10 newtons to the right. So let me switch over. So it'll be 15 newtons to the right minus 5, or 10 newtons to the right. So forces are vectors. Now we can rotate our vectors around. For the most part, we're not going to do perpendicular vectors like we did in the previous units. We're simply going to break them into x and y components. Let's look at this example right here. What do you do when I have 15 newtons going to the right? So that'll be 15 is positive because positive is to the right, right is positive. And then 20 newtons going to the left. That'll be minus 20 newtons. So my answer is negative 5 newtons. Or you could write it 5 newtons to the left, because vectors or forces are vectors. Now, Newton's second law is very interesting. We have already learned that all objects on the surface of the Earth have an acceleration. If we drop them, then they're going to fall with an acceleration of negative 9.8 meters per second squared. Galileo was the first to show that you could have equal accelerations, but if you had an unequal mass, it didn't make any sense. Why would two objects who had different masses fall at the same rate? Now, we can apply Newton's second law, and we can prove that all accelerations are the same regardless of their mass. We won't prove it, though. Now, clearly, as this man jumps out of this perfectly stable, he's on a ledge up here of this building. If his parachute is not deployed, he is going to fall at a rate of 9.8 meters per second squared. So right in there is his parachute. So he doesn't want to fall at that rate all the way to the ground. Now, let's talk about the difference in mass and weight. Your mass is a characteristic of how much matter you have, how much inertia you have. Your weight is actually a characteristic of where you are. Let's look at this. Newton's second law states F equals ma. You're standing on planet Earth. Your weight, okay, and we're going to call that Fg, is always going to equal m times g, where g is 9.8 meters per second squared. So for every kilogram, you're going to have 9.8 newtons of force acting on you because you're on the Earth. Mass and weight are proportional, but they're not the same. So Fg, so your weight, is equal to your mass times g. Mass and weight are proportional. That means they're directly across the equal sign from each other. And that proportionality constant is, of course, g. If we were to go to the moon, where g is significantly less, your weight would go down, but your mass would still stay the same. All right. Let's look at the scales of justice here. All right. We confuse mass, weight, and volume. Particularly if you've had chemistry, this should be cleared up. So let's just look at our units here. Mass is the amount of matter and always measured in kilograms. Weight is a force due to gravity, and units are always newtons. Volume is the amount of space. We don't tend to deal with this in physics. Now, Newton's third law. Whoops. As this shuttle is about to take off, we see examples of Newton's third law. This is the action-reaction law. Whenever a force is applied on one object, the second object exerts an equal but opposite force right back. Now the trick here is these act simultaneously. They occur at the exact same time, and they're on different objects. So if I say that I have a bat hitting a ball, the reaction to that is going to be the ball hitting the bat. Now, the action-reaction law means for every force, there's an equal and opposite force. So look at this man. He's pushing against the wall. The wall is pushing back at him. Okay? He's pushing the wall. The wall is pushing back at him with the same force. Okay? Let's go to the next page. We write it this way. F of man on wall is equal to minus the force of the wall on the man. Get this out of the way. Now, let's read the statements and see if we can figure out which law we're dealing with. If a car stops suddenly and you fall forward, it's not an action-reaction. It's not a third law because it's not you hitting the floor and the floor hitting you. This is really a first law situation. You are moving at a nice constant speed, all right? You're in your car here, and you're driving along, and you're going at a constant speed with the car, all right? And the car stops, but you still feel like you're going at the same speed. You push a piano across the floor with the correct amount of force. This one you kind of have to think about, and it kind of depends on how we're asking this. If I push and the piano pushes back with just the right amount of force, then this is an action-reaction. Now, just the right amount of force could also mean that we're moving at a constant speed. So an argument could be made for this to be both third and first law. Let's see. The more people enter a bus causes the mass of the bus and its contents to increase, so the driver has to push harder on the gas pedal. Okay, this is clearly a second law situation. Whenever a mass changes or an acceleration changes, or the speed, changes, then we're looking at a second law situation. Boy steps out of a boat. As he steps forward, the boat moves in the opposite direction. All right, this is clearly an action-reaction. You've got the boy on the boat on the boy. So that's third law. Now, magician pulls a tablecloth, and the dishes don't move. Huh. Well, the dishes have inertia. They're not moving. You remove the tablecloth, and they stay there. All right. Why? Because they don't want to move unless they're acted on by an outside force. Okay, let's practice a problem. Can you find your own mass in kilograms with the following information? You have a 1 kilogram, weighs 2.2 pounds on Earth. So, what's your mass in kilograms? Let's say you weigh 100 pounds. How will I find my mass? Well, this is some simple unit conversion we did before. If you weigh 100 pounds and your conversion factor is that 1 kilogram is equal to 2.2 pounds, then you line it up so that your pounds cancel and you're left with kilograms in the numerator. So 1 kilogram is 2.2 pounds. So multiply straight across and you get, if you weigh 100 pounds, then you are 45.45 kilograms. What's your weight in newtons? Well, if your mass is 45.45 kilograms, Fg equals mg. So your mass is 45.45 kilograms. And we're just going to use g as 10 meters per second squared. Sometimes that's easier to do in your problems than using 9.8. And you get that you have a weight of 454.5 newtons. All right. Claudia stubs her toe on a coffee table with a force of 100 newtons. I bet she broke it. What is the acceleration of Claudia's 1.8 kilogram foot? All right. Let's look at this. We have some information in here. We are given that the force applied is 100 newtons. The force on her toe on the coffee table is the same as the force of the coffee table on her toe. So our object here is going to be her toe. Apologize for the pictures. Here's her toe. There's the nail. There's the toe. All right, so there's going to be a force applied of 100 newtons on her toe. And the mass of her toe is 1.8 kilograms, so she's got a seriously big foot. All right. What is the acceleration? We're looking for A. We only have really one equation at this point, and that's F equals ma. We're looking for A, so we solve it. A is F divided by m. For a solution, we plug in our numbers. 100 newtons divided by 1.8 kilograms. So she's going to have a very hefty acceleration of 55.56 meters per second squared. So now, what is the acceleration of the table if the table had a mass of 20 kilograms? Same problem, only this time, same force. All right, we're looking at the force of between the toe and the coffee table. So now here's the table, and the table is 20 kilograms. All right, same force is being applied. Same force. So the givens are, of course, the force is 100 newtons, and the mass of the table is 20 kilograms. The unknown is the acceleration. Equation, F equals ma. Solve it. A is F divided by m. So the solution is the force is 100 divided by 20, or 5 meters per second squared. So let's look at this. Her toe would accelerate at 55.56 meters per second squared, while the coffee table would have an acceleration of only 5 meters per second squared. Now, how far, she stubs her toe, same coffee table, how far will the table travel in 1 second? Oh, yay, kinematics, here we come. We have a force, we have a mass, and we have an acceleration. We're looking, and we have an initial speed. The initial speed of the table is, of course, 100 newtons. It's not moving before she kicks it. The unknown is her displacement. Let's go back to our kinematic equations of motion. Delta x is v naught t plus 1/2 at squared. Plug in our numbers. V naught is equal to 0. Now, you can always, when it equals 0 like this, you can always bracket this whole thing and make it 0 and just not have to put this in. 1/2 times 5 times 1 second squared is equal to 2.5. Now, it's very important when you're doing these problems to make sure whatever number is in here, you square it and not the entire answer. And again, you don't have to put your units in the problem here. It sometimes gets a little bulky and confusing.